Scandinavian.
What?
Sounds the same.
Tonight I will go to the MSG and you oh, you are in the do you have any idea like 230 2 more lines? Where do they go for the
Like what you can choose.
no, how many people are there? Like PE or something. Then I was wondering like
Yes.
I mean I know how they from 2 5 they 2 4 then like just what but I think so big so yeah.
Oh, why did they go like
Oh yeah. They really only got 2 choices.
pure math choice?
Yeah, but no, that's fine.
Yeah.
Some of them they took like
Yeah, I know.
but if the whole class go to then it's possible that
Maybe that's like Chinese.
or maybe the Chinese or
Like Chinese. Actually, this.
But
Many time on God. And they do that's
I think still of
good.
then kill mess then
我们竟然找到了，
我差点死掉了，我又复活了，
你不要好嘛，
然后我又发烧了。
你可以吃那个vitamin C 的 tablet，比较快好，那个10块钱吧。Okay, something I want to address for Monday that we really haven't really thought about because we also skip those proofs is to argue why the standard loop with a different n is different loop. Why? Any idea about if you have a look at my proof before? How to argue? Why are they different? Can you find homotopy between different? Different S? What's S? S 是什么东西？So, right, wait, let me write down this formula here. So how do we define this path again? This is the path from e to the 2 pi I n t, right? So this is IMT, right? Yeah. So how do you argue that there's no homotopy between two back? Hold the hour. Their base point is the same fundamental. I don't know, I haven't tried, but if you can you like put some here and Sorry.
That's very good. 不一样的。
不一样的地方。leap，这个 leap，这个 leap，对 ，I think we can argue through leap. Okay, so how do we argue through leap? So I think this is really related on how we parameterize our circle here. So the parameterization we gave here was t to e to the it. So the full circle here is not 0 to 1 actually. It's actually 0 to 1 times 2 pi. That's why yesterday we divide by 2 pi, right? We take the endpoint divide by 2. Actually, it's not, but well, 2 pi times z is isomorphic to z. So that's why it's just that. But actually, in this parameterization here, we are using 2 pi. Okay, 0 to 2 pi. If you look at the Hatcher one, they already put their 2 pi into their p. So their whole round is really 0 to 1. Okay, so because our map there's no 2 pi here, so to get the whole round we need 0 to 2. Okay, and then multiple. Okay, so really you have a map from R to S1 here. So why I draw as a helix here is just a convenient way to tell you like when do we go back to the base point after mapping. Okay, and then these are the pre-image. Now, once I draw like a helix style, right? The pre-image is you can like cross it, then all the pre-image will be on that line. You can imagine what I say. So let's say I want to look at the pre-image of this line. You just draw a line and then cross it with the helix. Then these are all the pre-image. Understand or not? So for example, on this side, right? So this side is the pre-image of this. So for example, this point is, let's say we call it 1, 0. Okay. So these are the multiple of 2 pi on this line. Okay. So if you link these two to R, what happens? This Wn is a path from 0 to m times 2 pi. This path is 0 to m times 2 pi. So their endpoint is different. Where got homotopy between path of different endpoints? Forever. Okay, if you have a homotopy downstairs here, we already proved that there should be a homotopy upstairs. But then if you lift it up, there are paths with different endpoint already. So one of them is like 0 to n. The other could be 0 to maybe m. Okay, their endpoint is different. Okay, they start at the same point, but okay, why they start at the same point? This is actually our requirement. We want to leave all paths from the same point. You remember the Z0? We fix one. Okay, once we fix this boundary condition or this starting point, there's only one leaf you can get. Correct? There's only one leaf you can get. That is unique. Okay. Once you pick the boundary point or starting point, then there's only one leaf you can get. Okay, so that's why you get these discrete number of loops. Okay. Question? So you can't really see downstairs here. This is portraying how important this R to this S1. Okay. Later we'll call this kind of space as covering space. Okay. At the bottom you cannot quite see something interesting. At the top you will differentiate. Why you will differentiate? Okay, another thing come up from my discussion with Seng. So what's the point of R to this S1 actually? What's the point? Okay, the point is you can record your location, you also can record your time. And this is the point of this covering space. So you have more information in this covering space. Yeah, because if it is S1, you keep coming back to the same place, but at different time. How do I differentiate these two parts? So I differentiate by listing out the time. But it turns out that R is enough for this. And then actually R is the kind of the largest covering space for this. Kind of the largest one. Then later we will see what are the smaller covering space. All right. Since everyone is here, how about we take a quiz first? 哎，你哋要不要帮我拍一下？拍给有考试的人就好了。如果你不学他有没有在我们班，你问一下他。对啦，题目纸有没有被给出去啊？我题目纸不见掉。哦，在这里。Okay. So please write down your name, student ID, and today we got the second quiz. Okay, so there are two short questions here. What are the criteria for a simply connected space? For those who are just auditing, you want to try also can. Second, give a simply connected space and then explain. Okay, I give you 10 minutes. So that 我不会弄乱。Keep your laptop whatever thing Yeah, most of you stop writing. Okay, still need time. Okay. If okay, how about we exchange paper? Okay, so different role exchange with different paper. Maybe 你帮我弄弄可以吗？你帮我搜一下，然后乱派给他们，派给不一样的人。Yeah. 同一排的人就不要派回去同一排了。Yeah. Okay, I want you to who mark. Who mark. So mark each other paper. Okay. I want to see how you give mark. Who mark, and then I will mark also. You who mark first. 看一下你朋友的答案是长怎样的。Okay. We will discuss answer first, and then we discuss how to give mark, and then you will decide a mark for your friends. 对。OK，全部人拿不一样的，你收到了吗？还没有，他还没有，后面还没有，要换一个。Okay, so let's discuss answer first, and then we discuss how to give marks. 是外面变暗去啊，感觉有开灯关灯的感觉，刚才也是这样。要死我，这雨它很大哎。Okay, so question 1. What are the criteria for a simply connected space? Actually, there are two answers for this. Okay, so if you prove by definition, if you say by definition was two things, path connectedness, good, and then path connected, and then trivial. I just write pi 1, trivial pi 1. So simply it's just trivial pi 1 connected is path connected. And then second, if he wrote that there exists a unique homotopy path between 2 points also can, because this is what we proved for the equivalent property on simply connectedness. Okay, so either one of these is okay. Okay, second. Okay, so what do I explain here? So basically it's following the first question. You have to meet the first question criteria. So what I wrote here is every path with the same endpoint is homotopy to one another by very simple homotopy here, by a linear homotopy. So I write down the linear homotopy here. So well, so gamma st equals to t gamma 1x plus 1 minus t times gamma 0 ms. Why is it in R? Why this thing is in Rn? Basically, you just use the closure of Rn. I'm just multiplying, addition, subtraction. Everything is still in Rn. So the whole homotopy is okay. Okay, so this question is a bit maybe they will give different answer, but you need to check whether their y is true or not. Okay, so let's see how we give marks. So let's fix the total marks first. 10 or 20? Okay, 10. Let's fix 10. Okay, out of 10. So well, I'll give 5 lah. 5 to these two questions, equally important. Okay. So for question 1, if they wrote one of them, surely 5. Okay. But let's say no path connected but trivial only. No trivial. You think should give how many marks? 3. Wow. You are good to be a lecturer. Okay, for now, I will strict in quiz a little bit. Okay, so path connected is 2 marks. Trivial pi 1 is 3 marks. Okay, so I will put more focus on new stuff. Okay. For second one, how to divide? Any difference or not? I think the difference that we can do is here, existence and uniqueness. Okay, if existence we give 2 marks. If got uniqueness we give 3 marks. 2 plus 3. Okay. If just write homotopy of path, hey, got see people do like that, you know. Maybe you can give 2. Okay. Next one. I will focus more on explanation. Okay, so explanation will give 3 marks. A space will give 2 marks. Okay. So when you give marks, I want you to write in small part, because later I'll give my mark also. So once you give your mark, right, maybe you can do like this, something out of 5, and then write your name, sign your big name here, Adrian. Okay, put here 4/5, Adrian, like that. Okay, sign your name. Okay, do it now. Give you 1 minute. Maybe when I mark only 10 seconds. Yeah, give you 1 minute. Don't write too big because I'll give my mark later. Okay, let's see how you. Yes. Wow. Interesting. Got trivial pi 1. No trivial pi 1. Only connected. Only connected. Every group is homotopy. This one is pi 1, trivial pi 1. But okay, so let's think about it. So if you are lecturer, how to think about this? So they wrote connected but not path connected. Does connected imply path connected or not? No. So we cannot give 2 marks for sure. So the problem is how many marks we want to give. 1. Okay, good. 1. Okay, for now, maybe I'll give 1.5. But for quiz, we strict a bit. Okay. Yeah. Give 1. Okay, good. Good. Okay, give one. Okay. OK，答案，还有什么问题吗？答案太不一样了，还有问题吗？什么？
不是，你看那
一个字就有 connector 吧？就
这个句子的 connected
你说说看。
而且 the criteria for equal connection is basically the point connection something.
connector with something，至少他要再连东西啊，我们可怜他。一本，一本。来，哦，你讲，你不懂他的答案吗？哦，哪一个？linear path algebraic。他只是讲，他写的，你看他的词变什么？好词，他大概要写一点东西，他是写不清楚的。假设是从某东西来，感觉他只是在重复那个definition，可是他没有解释什么意见。但是他有讲 any two point 的这个我们有这个 linear homomorphism 的概念，但是他还不能把它完整写出来 homomorphism。他就不懂 homomorphism。没有，他知道那些点是可以被 linearly join 的，但是他不能够写出那个 homomorphism。所以你觉得呢？你决定啊，你决定一下，我让你决定一下啊，让你决定。based on 我的 marking criteria， 你决定一下。他写不出这个3分嘛，但是大概他知道有一个 linear path，就这样讲。不是跟你很像，你要跟我很像，你要跟我很像，不是跟你很。没有可怜不可怜啊，因为这些全部是我改的，所以你一定要 follow， 我们要你来。题目想要问你 ，OK， 可以吗？这样的话，一行啊 ，Help me collect all of them。有多少人啊？今天呢？1、2、3、4、5、6、9、10、11、12。OK， 这样我可以看一下你们改的比我严还是比我松。OK 啊，不要加纠结啊，10分嘛啊。什么？不会的单纯对。不会的单纯什么？不懂的单纯对改的。离谱！你不要讲啊，真的有这样的老师，你知道吗？真的，我没有骗你，我没有骗你，真的有这样的老师，改对就是了。真的，我没有骗你。等下次我们派回去，你知道你朋友给你几分？有人满分了。OK。All right, then we will continue with our lecture. So we'll continue to prove a few applications from this theorem here. So pi 1 of x1 is isomorphic. In this class, right, sometimes we will just write equal, okay? Because since we are talking about group, equal in group obviously is isomorphic. Okay, so sometimes you'll see equal in some literature. So please don't be afraid. It's just isomorphic. Okay. You know what's the difference or not? Being isomorphic and equal. Equal meaning equal on the elements. Okay, but you need to know that pi 1 of x is a homotopy class of path. Okay. loop or is particular, okay, based at certain point. So there are different elements, but they are isomorphic because their group structure is the same. All right. To continue with application, we shall define some new stuff here. Hey, by the way, if you find actual very hard to read, you can always ask me. Okay. And my lecture is try to like dissect the Hatcher stuff. Okay. Of course, with help of other lecture notes that I posted. All right. So we'll define what is called a retraction. So this thing is in the chapter 0 of Hatcher. So chapter 0, we don't purposely like just spend time on it. We will introduce while we go. Okay. So retraction of X onto A, onto the subset A, is actually a continuous map from X to X, okay, such that R of X should be A, okay. So you should, I don't know how to send, but it's a continuous map, okay, that send everything from X to A, okay. You should hit A, hit everything in A, and then everything in A should stay, okay. Everything in A should stay. So one thing you could do was, let's say you got an X here, okay, you got an A here, right? Okay, then you need to send this extra stuff into A, okay? And make sure that you hit everything in A. Okay, why am I circling? Yeah, okay, so maybe just slightly different. So this is X, and then this is A, okay, and then they map everything. Okay, for sure you can hit A because due to the second property here, because when you restrict to X, just X. So for the rest, you should send it. So that's why this is called retraction. Okay. All right, so from here, I'm going to prove one very classic theorem here. So this is a Brouwer fixed point theorem, but it's just 2D. For higher D, you can try and prove it in your project. I think Hatcher will give some reference. I'm not sure we will do it in course or either we won't do it. So you can try and take it as your project. Okay, so for 2D, what happens here? So every continuous map from the unit this to unit this actually has a fixed one. Okay, the statement is very simple. Whenever you want to construct a continuous map from D2 to D2, you need this in R2. Not necessary you need, right? Because we can apply topology. Huh? What is D2? Is disk. So D2 is a closed disk. Okay, so let's use the notation from general topology. So general topology, we tell you about B of like, let's say B of 0, B1, 0. And then if you close it, it's a closed ball, right? Okay. Well, you can take this as this with yeah, you can take this as a disk. But the disk we refer here is like topologically a disk. So meaning you can apply any homeomorphism. Okay, or not? Not necessarily radius 1 center at 0. You understand what I say? Understand what I say? Okay, so for example, your disk might look like this as well. Could be. Yeah, continuous is fine, right? Yeah, no differentiability. Okay. Anything homeomorphic to close this? Any other question? This notation come out in your assignment also, so better take note. All right. So proof. Well, how to prove this kind of equality? You suppose by contradiction. Okay, right. So you suppose on the contrary that HS is not equals to X. Because there's no fixed point, right? Okay. But you should think that we should apply similar trick as last time. Okay. What's the similar trick here? Oh, it's a different trick, sorry. Similar trick will apply next in the next theorem. But this is a bit tricky. This proof here is a bit tricky. So we can define a map which we call the ray map. Not ratio, ray map. Ray map from D2 to S1. So how do we define this? It's kind of tricky. So you take a point from D2, okay, you send it to Rx. So which point you want to send here? Well, I think let's draw it. Drawing is easier to explain. So let's say here is X1, right? The thing inside is D2. Okay, everything inside is D2. So we pick one point here. Okay, so here is X. Right. Okay, then because HS is not equal to X, so HS will be somewhere else inside D2. Okay, what you can do is you draw a line passing through them. Okay, you draw a line passing through them. Okay. Then meet 2 point here. Which point can we pick? Okay. We don't do this. Instead, we start with HS and then draw to X. And then you will certainly just meet one side. Okay, then this is our Rx. Okay. Here, write down this map precisely. What do you think? S minus X, and then what's your Rx? So how do you define Rx? It's not just HS minus X, right? HS minus X is it gradient? Not quite gradient. It's the vector. Is that vector? But you want exactly the point that hit on X1. So there's a length condition coming in. Okay, so there's a length condition coming in. It's not too far from this Hx minus X already. It's actually Hx plus T of X minus Hx. Okay, so meaning you start from Hx and then you add some length of X minus Hx. Okay, what's the length you're gonna add there? Actually, this subject to this condition, because you need to stay on where? Stay on X1, right? So you must be a unique factor. So solve this for T. Solve this for T, right? Connect. You can solve, right? You need to open up. Okay, yeah, a little bit of complicated, but it's not that not non-doable. It's doable. Okay, and then someone did it, not me. Someone did it, and then this is the solution. Okay, you can try and check is it true or not, but this is the solution. Let's try and solve that square thingy. This is the quadratic equation, right? So you need to use the b squared minus 4ac and whatever. You have to find this root here. Okay, choose one of the roots. So the claim here was so the claim is R is continuous. Okay, I think it should be obvious, right? For now, once I compute it, it's just a bunch of continuous function put together. And then second, so this is the first thing. C. Second, Rx actually equals to X if X is in X1. So if you describe, sorry, what did I say here? So, Does it make sense? Rx equal to x. Without looking at the formula yet, from the description, is it clear? So you start from anywhere in x1. Okay, you start from anywhere in x. Sorry, x1. And then hashes could be either inside, either outside, right? Okay. So one case is you draw from inside one to x, still x, still touches x. But if it is on another point on x1, you draw from hash x to x to x. Okay, so actually it's x itself. So this point on x1 is kind of the fixed point for this map. Fixed point. Okay. So what do we have here? We send every point in D2 to S1. Okay. And then everything on S1 is still on S1. This is a retraction. Okay, we retract D2 to X1. Okay, so by definition, so by construction, okay, by construction, R is a retraction of D2 onto S1. Okay. But we're going to show that this cannot happen. Okay, we cannot have this kind of retraction. Okay. You should think about D2 is something like field. Okay, it's something full. X1, there's a hole. How to make the hole? For example, on this paper, you need to pop it. Pop it is not continuous. Okay, so how do we construct this contradiction here? So we say just now already, we're going to use pi 1 of x1 is z. Okay, so let's use this fact here. So let gamma 0 be any loop in x1. Okay, so in D2, we can construct a homotopy of gamma 0 to a constant loop. Okay, we're just trying to homotop the loop in x1 to some constant loop in D2. This is possible because D2 is a convex set, for example. Okay. Or S0 a base point of gamma 0. Okay. Then we will do a hack here. Okay, so what's the hack here? The hack here. So let's see. So this homotop is from where to where? When time is 0, it is gamma 0x, so in x1. And then when time is 1, it is a constant map. Okay. Right. Okay. Let's see, huh? Okay, so next thing I'm gonna write is since the retraction R is the identity on x1, we claim that the composition R on gamma t is then a homotopy in x1 from R of gamma 0 to the constant loop at x0. Okay, let's think about this. Is this true? Well, the composition of two continuous functions is continuous. And then What do you need to satisfy for homotopy in S1? You need to satisfy for in X1. So for every t, this path should stay inside X1. And then let me think. But R is the thing that send you back to S1, right? Does it make sense? So when you do R gamma T, right? Wait, R gamma T. Position here. R gamma T. Okay. This R gamma T here. Let's draw it. Let's picture this. So this is your X. X. So this is your D2. This is your D2. Okay. And then you have a loops around here. So let's draw a loop. Oops. So you have loops here. Okay. Let's say you have a homotopy. Okay, homotopy to a base point. Let's say this is the base point, right? You have a homotopy. Okay. Make sense? Okay. Then for each homotopy here, you use the R map to send it back. Make sense? You know what happened R with this all this gamma T? Huh? R on this gamma T. So it will like use the ray property, right? It will use the ray property and then send it back to X1. Correct or not? Correct, huh? And then for the last point here, S0, we already say that if R act on the point of X0, it should be X0. So the last point is still X1. But for the middle one, at homotop, send back to X1. Homotop, send back to X1. Send back to X1. Send back to X1. But every stage, still continuous or right? Because it's a composition of continuous function. So this is the bug. We produce a homotopy in S1 such that a non-trivial loop is homotop to a trivial loop. So this contradicts the proposition we put, or the discussion we make before the class. Because non-trivial loops, you should leave up to a different endpoint, okay, than the component. Okay. Make sense? Okay. But these contradict the fact that pi 1 of x1 is non-zero. If this could happen, then our pi 1 of x1 will collapse. Okay. Understand? Question? Any question? Yes? Any question? Yes? I will send it back to S1. Yes. That's right. Okay. Through the ray map, you will send things back to S1. But now it's just composition, right? Composition is continuous. So it's a valid continuous map. Okay. For question? Yeah. Why do we want to construct retraction? Because we try to retrace the homotopy back to S1. Okay, we try to retrace a homotopy back to S1. Okay. B. Yeah, we try to retrace our homotopy back to S1. And then retraction is a continuous map. Yeah, I think another point you ask this question is, this also prove that there's no retraction from the corollary from this thing is there's no retraction from D2 to S1. Okay, this is the corollary. Okay, so it's like equivalent. There's no retraction. Contraction? I didn't define contraction. No. Didn't define contraction.
Shouldn't there is no retraction between two space with different homological group, fundamental group?
I think that would be more involved. Yeah, because here we are dealing with a specific retraction. Wait, let me think. Let me think.
Group is the same. Matter what the different space is. That's what it's doing. D square, if that is a homotopy to S1, then the no, not exactly only three.
Yeah, I think it's a different. I think it's a different proof. I think those are different proof. Yeah, because why I can claim, I just produce one retraction. Why I can claim for all kind of retraction is because, I guess you could show that every such retraction should be homotopy to each other. Yeah, the map are homotopic. Although we didn't define the map, I think we have a remark to ask you to define, right? So I think we could add that in, yeah, so that you know how to define homotopy between maps. It's very similar to homotopy between path because path is already mapped. Okay. Any other thing? Last. Okay. In this case, how about we take a break? Then let's break until 3:02. Oh, contractible. Yeah. Contractible. No. Contractible 是形容一个 loop 吧？呀，给我想想，这个是形容一个 function 从它去它自己。你那个 contractible 之后，我们还会再 define for space 的。呀，那天我们有大概讲到 for loop，但是我们会讲，如果一个 space contractible 是什么意思？应该就是每一个 loop 都，或者就是 simply connected。不一定不一定 simply connected，可能它不 part connected。呀，它就是拍 one 的 meaning space loop。等一下我们会理。那天我们是 contractible objects。啊？是。 什么？
但是你这个两个都是从这边过去嘛？
对
为什么这个好就是一个曲一个回这样子？
因为你想想看啊，如果我，哎，没有这个真的我画错，我忘记改是吗？啊，我忘记改这个错，应该改了吧？我改了，哎呀，check 一下，这个是我画错，这个是我画错最新的，我忘记 upload，我有人告诉我，然后我有改，你有看那个人家打的吗？你可以
没有
开两份也是，因为那一份我也有改，然后这一份我记得我改了，没有改，没有改。是看一下这边，可能我忘记 upload，谢谢你啊。
因为我刚一问，我刚看到时候就问，
哎，还没有改，
雷在卡5分钟，我就懵。
有人告诉我了，我记得。
对
OK，我会改一下。
对，这它还是一样照。
它是顺下去的，它是顺的，所以才会顺两圈嘛。
哦，对，它印象瞬间也是
对
对。
对，它顺两圈
可是。它这个如果它加 prime 的意思就是如果比如说，只因为它是两个，它从一个点开始，就是一个点开始两个圆哦，所以我就 b1 prime。如果比如说我从这个点我出3个的话，这样我就是 b1 prime 吗？
你可以这样讲啊。其实我加它 B1 也没有什么错啊。
就是两个 b1。
但是这里的重点就是来，我再把两个一圈的东西加在一起。
哦，
重点是这个1加1等于2。
OK。所以比如说2是指这个方向嘛？这样如果是
另外一个方向就 B 减2。
对，我们还没看下面那个减的。
嗯，是啊，你可以先，我觉得你可以先休息好，先。对啊，你没有休息好，等下一直不会好。 Okay, want to start first? 这教精英班挺好，精英班挺好。Okay, right. So next is Bossut-Ulam theorem. Okay, so this is the 2D version as well. So the higher version. Actually, I did this for my project last time when I was my undergraduate. Then my lecturer said I was too ambitious. Why I'm too ambitious? Because there's a lot of detail to prove. So I presented a lot of detail. So he think that maybe it's too long for his presentation. That's it. Okay, so if someone interested also can do this higher dimension. Also do long theorem. So what's this content here? Is everyone okay with S2? Yeah, S2 okay. Okay. So for every continuous map from X2 to R2, okay, so I draw there already X2 to R2. There will always exist a pair of antipolar points X and minus X in S2 such that Fx equals to F minus X. It's like an even function. Okay. There's a point that it acts like an even function. Okay. So there's a real life application for this. It just says that, for example, let's say the temperature is continuous. Should it be continuous? Cannot be like I pass through just like here is 冰火两重天, right? It's all slowly decay also later. So it's like continuous. So this explanation is like if you find opposite 2 points in the earth, there would be same temperature. Okay, maybe you can think of North Pole and South Pole. It's cold, right? Somewhat cold. Yeah, maybe one is colder than the other. They are cold. Anyway. So if temperature is continuous, then that means that there must be some antipolar point such that the temperature is the same. Right. Then let's prove this. So how do we find this x? How to find this x? Still, actually, we don't know how to find this x. Okay, we will just prove by contradiction that exists. Okay, we don't know how to find this x because this x should be depend on f. But what kind of f? I think they vary a lot. Okay, so we just prove by contradiction. Okay, yeah, suppose the conclusion is false. Yeah. 变激光. So we could define a map G from X2 to X1. Okay. So we also squeeze all the point to S1. How to squeeze here? So Gx is defined to be Fx, the difference between Fx and F minus X1. Okay. And then we want to make sure it's length 1. So we divide by the length. Okay. So this is a map from X2 to S1. Well, there's a loop around S2 as well. There's a loop. Okay. Well, let's take this loop here. So define a loop that circling the equator. Okay, for now we need some parameterization to work. So we cannot look at random x2. We need to fix it to be the unique sphere so that we have this equator here. Okay, we have this equator. Everyone happy with this equator? Cosine and then height 0. Okay, This pretty much depend on how we put the S2 in, because S2 is centered around origin. So the equator is on the XY plane. Okay. If not, you need to adjust yourself. But doesn't matter. It's the same proof. Okay. Now let hash to be the composite. So what composite here? We will do n first, okay, and then we will do g. Yes, okay, we'll do n first, we do g. So meaning what? We just restrict to this equator, see where this equator go in S1. Okay. So there's some property we had here. So note that if you put g minus x, okay, it's actually equals to minus gx. Okay, is it clear? Very clear substitution. This morning I teach substitution on function. Substitute, can substitute, right? G minus x. Okay. Well, this is good. Then there's next surprising stuff. Because our equator is periodic, kind of periodic because cosine are periodic function. So you can see that for every x is 0 to half, hash of x plus half is equals to g on eta of x plus half. Okay, which is equals to g of minus nx eta x. Okay, so by the property of g, we will get minus hx. Okay, so this is our periodicity. Maybe it's an odd periodicity because you have negative. Okay. For this half period here, well, okay, so let's draw this picture. So we got a continuous map from I to xi now. So let's consider it lift. Okay, let's consider it lift here. Okay, what's this lift here? Okay, if you still remember our lift, they have to commute together after composing with this special map, right? E to the IT. Okay, so whatever, how you lift your h, right? So by lifting h, we get hash tilde of x plus half equals to hash tilde x of q pi. Okay, for this q to be odd. This is how you get a minus sign, right? From exponential function. Odd pi, e to the I of pi, you get minus 1. Okay, but this q might be depend on s. So depending on x, could be depending on x, but doesn't matter. All that matter is it is odd. Okay, to get this minus 1 here. But in fact, it might seem that this q could depend on x, but actually it's not. And we will prove why it's not. Because since by solving for y, because q is what? Q is okay. Okay, just write down these few words. Because q live in a discrete set. Okay, and then we have a map from a connected space to a discrete set. So this q must be constant. A map from connected set to discrete set if q to be a constant. Okay, because S is a connected space from a connected space, and then hash is continuous. So this q value here must be discrete. Sorry, this q here must be constant because the choice of q is discrete. Okay. Right. So in particular, let's try and compute some endpoint here. let's see. What if what is H1 tilde? Okay, H1 tilde, if you use the formula above, it is just H tilde half plus Q pi. Okay, and then you can apply inductively, you get minus half again, you get H tilde 0 plus Q pi plus Q pi. Okay, but what does this mean? If you still remember our map from pi 1 to Z, this is H tilde 1 minus H tilde 0 over 2 pi equals to Q. What's this number means? This number tells you this H loops how many round. Okay, still remember the map? Okay, going from pi 1 to Z, 1 over 2 pi times H F tilde 1 minus F tilde 0, right? Okay. So since Q is odd, okay, we conclude that because the leaf here is odd, conclude that H is not null homotopy. Because if you want to be null homotopy, your Q must be at least 0. 0? 0. 0. You cannot loop. Okay, you cannot finish a loop. So that you are null homotopy. Okay. So where's the contradiction here? Where's the contradiction here? But hash is this composition. Remind us again. Going from x2 to x1. Okay. So we go from a unit interval, loop around the equator, and then go to x1. Okay. Well, not that eta is obviously null homotopic in S2. This one, everyone agree or not? So you draw your circle here, and then your null homotopic could be something like this, right? To the north pole. Can go to other pole also can. Not even pole also can. You can like loop around this, right? It's like you taking the 塑胶袋, right? You can loop around the ball. Okay. Rubber band, I mean. Okay, so eta is null homotopic. So you can use that null homotopic to directly say that G eta is also null homotopic. Because at first you already null homotopic to a point, and then you apply G again. Okay, then it is a null homotopic. But is this possible or not? Is this possible? Can you create a null homotopic? Okay, just now we said that it is not. Okay, so thus we get a contradiction. Okay, so the remark here is there's no one-to-one continuous map, okay, from S2 to R2. There must be 2 points sent to the same point, and these are the antipodal points. Okay, so there's no one-to-one continuous map from S2 to R2. So R2, X2 is actually not homeomorphic to a subspace of R2. Okay. This is what happened to the map, you know. Actually, the map you buy from the bookstore, from the roads, actually it cannot fully represent the Earth. I mean, in terms of measurement, in terms of topology, also obviously can, or maybe China is here, Malaysia here, right? But in terms of measurement, you cannot do that. And that's the way to compute that. And then that way will be done in differential geometry, which is curvature. Okay. This is why Gaussian, I think it's called Gauss curvature. Okay, Gauss create this thing to see what's the difference. Okay, how much difference from S2 to R2? Okay. Okay, so these are the about curvature. Okay, continue. Corollary here. Maybe I don't prove this. I left this proof for you. But the corollary is as if you break your S2 into 3 closed set, then one of the closed set must contain the antipodal point. Okay. So basically, you need to apply Borsuk-Ulam theorem here. So you need to think of one continuous map to use. Okay. So the hint here was just use the metric function. Okay. Infimum of y in AI with all the points. Okay, I won't prove these. Maybe you can ask a question, why 3 are not 2, not 4, not 5, or yeah. I think you can read through the proof and then it will make sense why it is 3. It's some logical statement actually. Okay, you put some calculation and then put some logical thinking, then the number has to be 3. Okay, you try and read the proof, it's not too hard. But the proof is to use Borsuk-Ulam theorem, so you need a continuous map to start with. Okay, one very important proposition here was if x and y are path connected, okay, then pi 1 of x cross y is actually isomorphic to pi 1 x cross pi 1 y. Okay, you can try to prove this. Any idea how to prove this? Isomorphic, right? You need to produce the map. What's the map? What do you think? What's the map is? The map is. So you need to take one loop in the product space, make it 2 loops, one in A, one in B. Is it possible? This is a question about general topology. Because a loop is a continuous map. So to specify a loop, you specify a continuous map. So how do you specify a continuous map on the product space? Yes. In what? 2 loops. Sure, we want to do that, but so a function, okay, if you're going to define, let's say, from a z such that z is in x cross y, right? Okay, well, really what you do was you tell me the 2 coordinate, right? So one is f1, what you happen to f1x and what happened to what happened to x and what happened to y. And then you use the f1x, f2y will form the loop in the corresponding space. Then what you need to show was, why is it isomorphic, group homomorphism, right? Then you're done. Okay or not? Okay. Any question? No. Okay, so we could see that actually pi 1 is kind of productive. Okay, so you can apply product space because exactly about continuity. So examples here. So for example, we will know what is pi 1 of x1 cross x1. Do you know what's x1 cross x1? Not r cross r anymore. Huh? Okay, so until 3rd year, finally you see something other than r cross r. What is x1 cross x1? So if r cross r meaning every r, right, you put one line r. But x1 cross x1, every point you put one circle. So what is it? Every point you put one circle. What is it? This is the empty donut. Okay, this is the empty donut here. Okay, so here trying to say that the pi one of the donut is z cross z. Okay, so if I gave you a donut, where is the generator of z cross z? Okay, let me ask you, how many generator z cross z has? 2. Why? 0, 1, and 0, 1, 1, 0, and 0, 1. You can choose the other generator, that's fine. But can you see there are two non-trivial loops? They are not homotopy to each other in this donut. One of them is you go around this loops here, this hole I mean. The other one you go around the longitudinal direction. Okay, so these two loops is not homotopy to each other. Can you imagine or not? Do we have donut here? Something I have. Okay, so you cannot, if you think of this as a rubber band here, if you put this rubber band here, the only thing you can do is loop around here only. You cannot really bring it out. Okay. Similarly, for this rubber band here, you can only like surface through these surface. Can you imagine the surface? Surface through these torus, but you cannot make it cut through this longitudinal part. Yeah. So like, how should I imagine that? It's like if you can you imagine a vector space like this? Sorry, vector field on this surface here. Yeah. Yes. Okay. Does it make sense? 我没有工具经理。Maybe if I found something, I can show you next time. Can you imagine? 我没有donut，还有 donut 比较好，因为这个 donut，下次啦，我想一想。Okay, so well, we can put more donut together. I don't know how to draw it, but if you take product of x1 n times, you get z to that. Yes. Okay. Okay, good. So this is about product set. Next, I would want to talk about some property of fundamental group, which is kind of categorical, but it will be the same treatment like how we treat polynomial maps. I'll tell you, we will focus on the property instead of these abstract definition. So we'll talk about functoriality of a fundamental group now. So what's the functoriality we're going to see here is, let's start with continuous map between topological space. Then we're going to construct, let's look at the last line here. We're going to construct a map from pi 1 of x to pi 1 of y. Okay, so we need to fix their base point. So how do we decide the base points, right? Not base point, base point. So first of all, we fix our base point at x first, and then the base point at y should be just f of that. No, f of that x. No. Okay. So the point here is, if I have a loops in x, okay, supposedly I should have a loop in y. Okay, that base at fx. Okay, does it make sense? Make sense or not? Because a loop is just I to x, right? Okay, I tell you how to go from x to y, so it should be I to x and then x to y. So it's a composition. Okay, so you do gamma first and then you do f. Yeah. So this is a function composition. So please don't confuse with the loop. It's a function. So you do gamma first and then you do. Okay, so this is the right place, right? I to y. Okay. Endpoint, I think, is not hard to choose and not hard to think about, right? Because if you start with x naught, end with x naught, obviously you map by f, you should go fx naught. Okay, so it's a loop. Okay, continuity should be obvious, right? Because F is gamma is continuous and positive. Of course, you need to check well-definers, or leave it for you to check well-definers. Okay, so then we will call this F star here, F lower star here, an induced map. Okay, so a map on topological space induce a map on fundamental space. Okay, fundamental group. Okay, happy? Okay, so where's the Functoriality here? To talk about this nonsense, I need to tell you some category theory first. So I want to define what's called a pointed topological space. Okay, so basically pointed topological space is start with topological space, and then pointed mean I want to pick the base point. Okay, so call it X point here. And then we will build a category. So category basically need two data here. Okay, one data is object, the other data is morphism, meaning maps between objects. So objects of this P top here from the topological space is just topological space, pick one point. And then how to go between these two spaces? Well, obviously you need to start with a continuous map F from X to Y. To Y. So Y become F here. Okay, to Y. Then what's the Y naught? How you fix the Y naught? Obviously, you need to pick the Y naught such that F of X naught is Y naught. Then only it works. Then how to compose? It's a usual composition. And then this is what we call a category of pointed space. So what kind of functor is this F is doing here? So this is the statement here. So let me see. Okay, so the map here. So you can see that for every object in the pointed topological space, right? In the previous section, we can build a fundamental group for it, just to consider all the loops from homotopy class of loop. So you can think of this a map between category. Okay, because pointed topology is a category, group is category. Okay, which is object is group, morphism is group morphism. Okay, and then I need to tell you what this map. If I need to tell you what is functor, I need to tell you what it does to object, what it does to morphism. Okay, so on morphism level, what to do? If we have a function between topological space, we can induce a map on pi1 as well. Okay, so that's why we have a functor here. Anything that can do these two things here is called a functor. Moreover, we got something called the covariant functor. In the algebraic geometry, you get a contravariant functor. So here is a covariant. Okay, so covariant refer to which part? Actually, it's this part here. Okay, covariant refer to this part. GF star equals to G star compose F star. Contravariant, GF star equals to F star compose G star. It could happen. So if it happens, it's a different thing. Okay, so in this case, we get a covariant. Can quickly check this condition here. Maybe we can quickly check this condition. Let me see. Yeah, how about check this? I think this one is quite useful here. Maybe quickly check this. So F is going, let's say, going from X to Y. Okay, and then Y is going from, G is going from Y to Z. Right. Then what's the induced map from X to Z? Okay, so meaning if I gave you a map from I to X, how to go all the way to Z? Okay, basically what you do was you start with your I to X, and then you do what? F star, do F, sorry, and then do G. Okay, so it's in order. You do F first and then do G. So is it clear that Y identity on topological space induce identity on fundamental group? Because if you have a loops, next, you apply identity, what do you get? You get the same loop. So it's the identity map on pi1x. Okay. Should I introduce category theory here? Because I think some of you didn't take algebraic geometry, right? But I did a little intro in general topology, right? What did I do? I just introduced definition of category. Did I do Funter? No. No. Huh? Then I need to prove the definition here. Because we will recall this definition in homology chapter. In that chapter, there are more Funter. You can even see natural Funter. Okay, I will put the definition here first. Okay. Okay, so the point I want to bring out this abstract nonsense is actually these two identity is pretty important. Okay, you need to know these two. If you forget covariant funder also can, but you need to know these two identity here. Okay. Oh, moreover, this last point here, moreover, if F is a homeomorphism, so there's an inverse, then the induced map actually is a group isomorphism. Okay. Sound very natural. Try and prove this. I think this is a good exercise. Okay, you can have an inverse map back. It actually tell you how to construct the inverse. Okay, any question about this comment here? This categorical comment. I will put the definition of covariant functor and category in front here. But I will give more example in the homology chapter. All right. Okay, next lemma. I'm not gonna write, but let's look at this. Let's dissect this paragraph here. If a topological space X is a union of a collection of a half-connected open set A alpha, each containing base point X naught. Okay, you start imagine we got X. Okay, I got a lot of union of half-connected open set, but each of them contain X naught. So that means their intersection is non-empty. Okay, must contain at least one X naught. Moreover, this is a very special condition here. Later we will incur this kind of condition again. Their intersection must be path connected. So meaning within A alpha itself is connected, their intersection also have to be path connected. Then every loop in X at X naught is homotopic to a product of loops, each of which is contained in a single A alpha. Can you imagine what is this trying to do? So let's try and draw this. Let's do the case for 2. Okay, so maybe this is okay, how about just draw 2 of them? So here is A alpha. Here's A by A beta. Okay, and then there's an X naught here. Okay, it's path connected, right? And let's say every loop in X at X naught is homotopic to a product of loop, each of which is contained in a single A alpha. All right, so there's some example in your text. Maybe how about we do something like this? Yeah, I think this is what is in actual, I guess. Wait, my arrow. Wait, what should I do? Okay, now good. So in this case here, this is a loop in X. Let's say our X is just union of these two. But the point here is you can write as a product of loops in each A alpha. For now, right? Is this a loop in A alpha or no? No, because you have to pass through A beta to form this loop. Is this a loop in A beta? No, no. You have to pass through A alpha to form this loop. But the point here is you can make it such that every part is a loop in contain exactly one A alpha. Okay, can you think of it how to do that? Read the coordinate. How do you? I want to write it as a product of loop. So from one loops, maybe you want to build 2 loops, 3 loops, 4 loops, such that all these loops live within one A alpha. How? It is related to your A1 midterm. A1 midterm or this one? Huh? Conjugation. Conjugation. Because yeah, conjugation. I give you some hint first. Conjugation. Give you some hint. What's the problem? The problem is I must pass through the other A alpha to get the loop. Can I become a loop before going to the different A alpha? How? You can make more loops. The game is you can make more loops, but how? Make more loops, but still stay as the same loop. Huh? Something like that. So 要动到谁？动到 A beta 再回去，应该是不要动到 A beta 就要回去了嘛，对不对 ？Correct or not? So let's say, your idea? 走，然后哪里上面这个东西，这个加在一起 ，OK，instead of 加在一起，we can directly produce a path here, okay? So we can go around and then produce a path here. We can connect here, this path here. Let's call this path a G1. Okay. And then I can go backward, and then continue my path again. And then you can see that if I go forward, go backward, these 2 paths actually cancel. I mean, not cancel, but contractible. Okay. And then I go down here, and then can go up again. Get G2, and then go down. Okay, and then go for the whole thing. Okay, let's give them some name. So what name should I give? So let's say this one is F2, F1, F3, Then I can write my F1, F2, F3 as what? I do F1 first, and then I do G1, and then I do G1 inverse, and then I do F2, and then I do G2. Okay, I think this is not quite conjugation, sorry, but quite close already. And then G inverse, and then F3. Okay, so for this 3 part here, they will live in alpha F1, G1 live in alpha beta, and then the next one live in, sorry, alpha beta is beta, and then alpha A alpha, and then this one live in A beta. Okay, no. Now the technical point is, why can you cut like that? Why can you cut like that? How do you know where to find the cut, or why can you do that? Okay, the point here, you need to use the Lebesgue lemma. You need to use the compactness of your unit vector. To still remember the Lebesgue lemma, you can chop your interval such that the image of that subinterval will live inside one of the A alpha. Okay, you use that to deal with the technical part. Okay, the idea is this. Okay, I don't write down the full argument. You can try and read. Okay, next. So next proposition, what we're gonna prove is for all n greater or equal to 2, pi 1 of xn is actually 0. Okay, this is pretty important. This will tell you that pi 1 is useless for Sn. So there's something more useful, which is pi n xn. Okay, this will be the last topic if we got time. Oh, never mind. Pi n is a homotopy here. Okay. Okay. So you can think of like pi 1 is like putting a x1 into it. Pi n Sn. Okay, so you can think whether you can put a S2 inside a space or not. You can think you can put a S3 inside a space or not. Like that. Okay. So how to prove this? This proof is kind of interesting. So let's do it. So proof. Well, we can split our Sn into 2 open sets. Okay. Each of one piece is homeomorphic to Rn. So for example, for S2, right, you can think of it, right? Because for example, we can like pick the upper half hemisphere, okay, and the lower half hemisphere. But their union have to be the everything, so you might need to thicken it a little bit. Okay, you might need to thicken it a little bit. Understand? Understand? Because it's an open set, so to cover everything, you should overlap. Okay, you should overlap. So where's the overlap? Maybe overlap here. Okay, you should overlap a bit. Does it make sense? Okay. So this A1, A2 here are open, right? So A1, A2, they are open, open, open. Okay, such that A1, A2 actually homeomorphic to R. Okay, in this case, Rn. I just use S2 to illustrate. And what's their intersection? Okay, their intersection should be xn minus 1. Okay, homeomorphic to xn minus 1. Okay, so in this x2 case, it is S1. Okay, when they overlap, it's like overlap at the cylinder. But cylinder is homeomorphic. Homeomorphic to X1. Okay. Homotopy. Homomorphic. Homotopy. Homotop. It's not homeo, right? Because no. It's a different concept. Did I define two space to be homotopy or not? I only define two paths to be homotopy, right? Let me think. Is it possible for a cylinder to be homeomorphic to X1? Can or not? There's no width for S1. Let me think. Can we? I don't think we can. Huh? Like, okay, so the intersection of A1 and A2 should look something like this, right? It's like a can without top and bottom. And then how is it the same as circle? Squeeze, Then, okay, in that case, you should think of this as an open interval. Is open interval same as 1 point? I don't think so. Hey, what's this sign here then? I'm wrong. Actually, cross the R. Sorry. Yeah, I need to cross the R. Okay, this makes sense now. Okay, sure. Okay, so Sn minus cross R. Okay, now it makes sense. Okay, so actually this AB is homeomorphic to R. Then okay, yeah, this is okay. Okay, it's not just Sn minus 1, it's Sn minus 1 cross the R. Okay. Because if you think of the x2 case, this is the intersection. It is open, so the boundary is open. The boundary is open.
That's hemisphere.
Yeah, hemisphere, but you need to overlap the two hemispheres because it's open. You cannot exactly meet at the intersection. Otherwise, you will miss an extra.
It's a little bit over.
You need to thicken. This is what we say, thicken. Thicken the hemisphere. And go a bit further down or up. Okay. All right. So far, so good. Okay, now we're gonna choose one base point from here. Let's choose a base point from here. Let's choose a base point. Call it x0. Okay, from the intersection. Put a base point there. All right. So what we do next? If n greater than or equals 2, then A1 intersect A2 is half connected. Okay, think of it, is this true or not? If n greater than or equals 2, it is s to the 1 cross r. Okay, so it's half connected. But if n equals to 1, what happened? It's s0 cross I. What is s0? What is s0? 2 points. One is at 1, one is -1. Correct or not? So what's the definition of xn? Is a unique one length point from the origin. Right? So s0 is something in R. Okay, so what's the length 1 point in R? There's only 2 of them. -1 and 1. So it's not connected. For the rest, it's connected. Okay. Well, by the previous lemma, it implies that every loop in Xn, we can kind of homotopic to loops, to product of loops in A1 or A2. Correct or not? Okay. But what are the loops in A1 and A2? What are the loops in A1 and A2? A1 and A2 trivial loops. There are only trivial loops inside there. Okay, so meaning you are composition of trivial loops. So hence every loops in Xn is actually now homotopic. Okay. Yeah. Okay, instead of I produce the now homotopy for you, I try to push this homotopy to different part of Rn. Okay. So another corollary is you can show that maybe we don't show here. So we could show that for n not equals to 2, R2 actually is not homomorphic to Rn. Okay. Homomorphic. This is homomorphic. Sorry? Yeah, continuity, yes. Okay, you can try and think about this. Maybe we can talk about this again next time. Okay. Any question? What is this part connected with the functor? No, nothing. Oh, that's what you want to mean. Let me see. Well, yeah, kind of. Yeah. Okay. You think that I should give a name to this part, is it? Okay, I'll try and do that. Okay. Any other question? Any other question? Other question? Okay, if no question, so please do the assignment And then Larry will be typing this week notes, right? And then I guess Eric will come up with the template today, tomorrow, today, without solution today. Okay. All right. Tonight I have office hour. I will be there at the MSG when 105. Okay, so you can meet me there. All right. See you next week. Yeah.